How are you guys? Today we'll learn two easy algorithms for finding minimum spanning trees. What's a spanning tree? Don't worry. Along the way, we'll learn important concepts as well. So specifically, we'll learn about greedy algorithms. The two algorithms that I said we'll learn today are examples of greedy algorithms. I'll also revise concepts that we discussed before. Brute force algorithm. This is a formal definition of greedy algorithm, but I think it's a bit confusing at this stage, so we'll come back to it later. So this is like one of the many problems that we use in learning problem solving techniques, paving a city puzzle. So the story goes like this. Once upon a time, there was this city that had no roads, no tar roads, let me put it that way. And getting around the city was particularly difficult, especially after rainstorms, because the ground became very muddy. So the mayor of the city decided that some of the streets must be paved, but didn't want to spend more money than necessary, because the city also wanted to build a swimming pool, prioritizing scarce resource. So the number of paving stones between each house represents cost of paving the route, each route. There are multiple routes that can connect all the houses, but paving stones, the cost of paving stones vary. Let me show you again. So for example, to go from this house to this house, you can go this way, you can go this way, etc. But the cost varies. So there are many routes, but the cost varies. So the mayor specifies two conditions. Enough streets must be paved so that it's possible for everyone to travel from their house to anyone else's house along a paved road. Enough street must be paved. And the paving should cost as little as possible. Like I said, the number of stones between the houses relate to the cost to pave the road between the houses. So the problem comes down to figuring out the least number of paving stones needed to allow people to get from any house to any other. So remember that this is not finding the shortest or quickest flight between two places, because that problem has another solution. Rather, think of it as finding the lowest cost when flying between two countries. Yeah, so for example, if I want to go from South Africa to my country, to Ethiopia, there are direct flights which are expensive, but there are also less cheaper flights, for example, that take very long time. So this is what we are saying. We want to find the lowest cost, not like the shortest path, which is a direct flight in this case. So to repeat, we are not focusing on finding the shortest path between each and every node in this problem. We rather try to find the lowest total cost which connects all nodes. If I ask you to do this, how do you start? Obviously, you would choose the smallest, like this, right? And then like this. This is also another shortest. And this, and this, and this, and this. Let me stop and ask you one question now. Have we paved enough roads to connect all the houses? I don't think so. These two houses are not connected to the rest of the houses, so we still have some more to go. So looks like I think we have connected every house, right? Yeah, we found a solution. So, and the total cost is 23. So it cost us 23 stones. Is there another solution? Let's see. Yeah, there is another solution. And instead of going this way, we can also go in this way. This is another solution with the same total cost. Another solution. Again, total cost is 23. Oh, look here. For example, to connect these two houses, how are we going now? A person from this house have to travel from here to here and here. But we could have connected these two houses with just 3 stones. So anyway, there are so many solutions. So the problem now is, how do we represent this in a computer? So doesn't this graph look like our Medicity? It seems like it's a good representation. From mathematics, we know that graph like this is a diagram representing a system of connections or interrelations among two or more things by a number of distinctive dots, the dots representing the things, and lines, bars, etc. And we can use it to represent our problem as well, as you can see. This is a good representation for the Medicity problem, right? Yeah. So what do we do now? Remember computational thinking. In computational thinking, we capture the essence of the problem using abstractions. So in this case, in a graph form. So let's learn some concepts about graphs. A graph consists of nodes, also called vertices, and edges, the lines that I mentioned, arcs or lines. Each edge joins two nodes. If the edges are labeled with, some figure or weights or cost, it's called a weighted graph. So which means there is an unweighted graph as well. And if all the nodes are reachable from each other, the graph is connected. So all the nodes are reachable from each other. You can reach from this node to this node in any way. So that means it's connected. If the edges are one-way arrows, the graph is called directed graph. So if there was an arrow pointing to one direction, then it means directed graph. So it means it's a directed graph. But otherwise, it's called an undirected graph. So this is in our case, we have an undirected graph. The edges have no orientation, which means like you can come from this edge to this, you can come from this node to this one, or the other way. Remember, this course is about computational thinking, right? And one aspect that we learned about computational thinking is the use of abstraction. So abstraction is about ignoring the unnecessary for our purpose details of the problem, right? So here the graph captures the essential core of the problem. This is a representation of the problem. Okay, so for example, in this particular example, what are the unnecessary details in this picture that we ignored or we didn't consider? Pause the video and think about it. Yeah, we ignored, for example, like we don't need to know if a particular house is a bungalow, a one-story building, like this one, a small house, etc. We don't care whether there is a bridge that we should cross or whether there is a park that we'll see when we travel in that direction, whether the road is hilly, or not, etc. Are things we are not considering. So by the way, they may be important. These aspects may be important for other cases. I mean, like they can be requirements for other problems and affect our decision of selecting our paths in those situations. So anyway, this is what we avoided in this particular case as some unnecessary details. So the aim is finding the lowest total cost. Yeah, so what can we do after performing abstractions to solve a whole family of this kind of problems? Another concept that we learned in this module is generalization. Abstraction can sometimes generalize a problem since it hides irrelevant or unnecessary details, because we want to use an algorithm in all similar problems, right? Generalization. How can a technique work for other problems too? Obviously, by using a notation that can be applied to similar constructs. This can be used to create an algorithm. In this course, in CSC 101, our focus is like on graph abstraction, and we only cover theory of computation. But the notation part, how you represent a graph, for example, for the purpose of writing a program, is a scope outside of this course, and it will be covered in second year, more in second year. By the way, I have included a note about graph theory in the course page. Please read it to see how we can apply it to different sets of problems. So applying graphs can help us to solve, to use the same algorithms to various similar problems. For example, a graph form can be applied to MDCT, some networks of nodes in the internet, connecting flights that plane takes between cities, the water pipeline problem in the campus, etc., etc. So by abstracting and generalizing, algorithms can solve a whole family of related problems. Let's now see some basic terminologies. A subset of edges is a spanning tree if it connects all nodes in the graph, but no cycle exists. So what's a tree in the first place? Think about it like any tree, natural tree. It has a root, a trunk, and branches, but as you all know, the branches are not connected to each other. So in a graph, in a simple term, a tree is simply a hierarchical graph with a root node and none of its edges forming a cycle. By the way, a graph can have various trees, right? Yeah. And a tree that contains a subset of edges of a graph is called a spanning tree. So as we saw, a graph can have various spanning trees, and we call a tree a minimum spanning tree if the total cost is actually small or the cheapest. So the question behind the muddy city problem now becomes find edges that are part of or constitute the minimum spanning tree. Greedy algorithms. Like I said, a graph may have a large number of spanning trees. The question is, how do you think we can get the minimum spanning tree from this list of trees? Let me ask you another question. What did we do in the previous lectures, for example, when we want to find solution for other puzzles, like for example, the river crossing problem? What we did was actually finding all the solutions exhaustively first, right? And then choose the best solution among them. Correct solutions, right? This approach is called brute force. Remember, we talked about brute force. So we can also do the same here, right? Yeah. But the problem is, in case of graphs, finding solutions using brute force will be very, very difficult. In some instances, the search space, the solutions, the options for finding the best solution could be like in finding from millions of options. So for this purpose, we need to follow another approach, and this approach is called greedy approach. The best explanation of a greedy algorithm is the coin change problem. Please, by the way, please Google it, and you can read about that problem. But let me quickly describe it to you. So imagine you're a coin changer and someone comes with a 20 rand note to get coins. What would you give him? How many combinations are there? For example, you could give him like 210 cents or 110 cents and 205 cents or 21 rand coin or 4 or 5 rand coins. You can imagine that the number of options are enormous. But what if the user wants us to have as much as possible bigger denominations? So we give him like the bigger denomination first, right? And then the next bigger denominations. For example, in this particular case, we'll give him like 4 5 rand coins. But if the amount that he was looking for, a coin for 23 rand, equivalent to 23 rand, then after giving him the 4 5 rand coins, we'll then give him the next denomination is 2 rand. We'll give him 2 rand and then 1 rand. So this is how greedy algorithms work. So in general, brute force algorithm is not feasible in some situations like this. And we have already seen, a problem-solving approach called divide and conquer, but this doesn't help. So that's the reason why we have this one. So in graph, in general, finding minimum spanning tree is not that easy, and there are some greedy algorithms that we can use. So we'll see uh, two of them here. So I will explain them in the next video.